Good morning, everyone. So let's come back to this problem we skipped from chapter 4, and then we'll look at that chapter 4 review packet that I posted. Just out of curiosity, how many of you guys were able to take a look at that review packet of problems? It's okay if you didn't. Okay. So we'll take a look at some review problems from chapter 4. Okay, so which compound here, which compound here has a chlorine atom with an oxidation number of +1? So this will just make us go through and assign oxidation numbers. The first one I'll start with is Cl2. Anytime we have a substance in its elemental form, where it's not in a compound, the oxidation number has to be 0. Think of it this way: if one of the chlorines is 0, the other has to be 0. The overall charge of chlorine is 0. So we can't have chlorine as -1 or +1 in Cl2 because then the molecule would have had a net charge. So 0 for Cl2. For HCl, our usual rule for H is +1 in molecular compounds, which this is. Sometimes we get a little confused and we might think HCl is an ionic compound. When this thing dissolves in water, it goes to H+ and Cl-, but it's a molecular compound though, and it's when it's actually bonded together. And then that means H is +1 in terms of its normal oxidation number, and then Cl would be its ordinary oxidation number of -1. And so if we then look at NaClO, that's sodium hypochlorite, that's the main ingredient in bleach. So sodium +1, Cl and O, ordinary charge for oxygen would be -2. So here's that chlorine with the +1 oxidation number. So we can deduce this +1 charge here just from summing up these oxidation numbers to get at the neutral charge that the molecule should have. And so B ends up being the right answer. Now what about chlorate ion in answer A? The oxidation number and charge of calcium is +2. The overall charge of chlorate is -1. So ClO3 should have a minus overall charge. Oxidation number of each oxygen should be its ordinary count of -2. There's 3 of them. So -6 from the 3 O's. And so chlorine should be a +5. So we can subtract 6 to get that -1 overall charge. So you have a +5 oxidation number of chlorine and ClO3, CaCl3 with 2 of them. Now if we want to double check, or something else you could do is think of the entire formula here. So if we're thinking again, oxygen's -2, if we want to double check for the whole formula, we have 6 oxygens, that's -12, meaning that we should have a +10 from the 2 chlorines, +10 because we have +2 here, +10 for +12, subtract the 12 to get overall neutral for CaCl3, 2 should be overall neutral. And so there's 2 chlorines here, 10 divided by 5, or 10 divided by 2 is +5. So just 2 different ways we can work through a double check that the oxidation number of chlorine in answer A would be +5. Okay, I wanted to point out this chart. I was quickly talking about this chart here on how this is showing us a relative sort of activity of different elements that are shown here. The elements at the top are the most reactive, meaning they're most likely to undergo their loss of electron oxidation reaction, where the metals at the bottom are more stable, less reactive, and so they're more likely, if they were in their cation form, to want to try to go back or reform their metal forms. Another way of thinking of this would be that gold is very unlikely to form gold ions in solution. So if you were to take like a gold ring, put it in a solution of acid, where acid's right in this little group here, if we imagine taking gold, placing it in a solution of H+, nothing would happen, which is good because we wouldn't want gold or our precious metals dissolving in corrosive water. So that's good that that wouldn't happen. But if we were to take lithium, potassium, we did the reaction of potassium in just water, but if we put potassium into a solution of acid, then what's going to happen is the acid is going to want to return to H2, and it's going to float away from the solution as the potassium then goes to K+. So we can take our metals at the top and then of this chart, and they're going to dissolve into the solutions of the cations below them. So we could dissolve, barium in a solution of sodium cations, but we couldn't take the opposite. We wouldn't be able to take a solution of barium and dissolve it with sodium. We couldn't dissolve sodium metal in a solution of barium. Now, we're not going to test you in the activity series. You're going to see some examples of this in lab, so you'll hit this series in lab. I wanted to point out here that the particular questions like, will zinc sulfate dissolve, will copper dissolve in zinc sulfate, or will zinc dissolve in copper sulfate? You might see some of these questions. You might see them in lab where you'll be, where you'll have them on problems that you need to solve. But for exams, we're not going to test you on those particular types of questions. Now, in case you're wondering, you just would look at, you would want the metal to be higher than the cation in order to react, is the basic answer to the question, in case you were just wondering. So you would want to find, like, if copper's here and zinc is up here, then zinc is here, then the zinc metal would dissolve in the copper solution, not vice versa. We could not take the copper and dissolve it in the zinc solution. Okay. And so then gold doesn't dissolve in HCl like we were talking about in the previous slide. So if I were to test you on this, I would have actually gotten a little demo to show you that this happens. I would have even put my ring in acid just to make sure it didn't dissolve. Okay, so let's get on to some questions just to review some topics from chapter 4, just to kind of make sure that we're maybe able to look back at the early part of chapter 4 and still put some of these topics together. So which compounds are strong acid? And this is really just something we have to know. So you have to know the strong acids are HCl, Br, and I. It's HNO3, ClO3, ClO4, and then the first H from H2SO4. So those are our 7 strong acids. Now, if we know those 7 strong acids and we know all the other acids, we learn how to name our weak acids. So that's why it's helpful to know these are the 7 strong acids. And so of these choices, only chloric acid here is the strong acid. And sulfurous acid would be a weak acid. What term best describes acetic acid in aqueous solution? So acetic acid is going to partially dissociate into acetate ion. An H plus ion. And so it's going to do this weakly. It's going to do this with a equilibrium. It's going to do this to not 100% yield because this substance here is a weak acid, not one of the strong acids. And so it also only would release this one H plus ion into solution. These H's stay intact. So these hydrogens here are not acidic at all. And that shouldn't be too surprising. Like if you look at something like methanol, has hydrogen atoms that aren't, none of these are acidic. So this molecule here is not an acid at all. It's not an acid or a base. So a base should release hydroxide ions. So CH3OH kind of contains H's that aren't acidic, and it also contains what looks like that hydroxyl group that also doesn't release into a solution. It stays intact, attached to the CH3 group. So I'm just merely pointing out that just the presence of hydrogens on a formula doesn't mean that those hydrogens are acidic. So we just have a monoprotic acid. So we have a weak monoprotic acid. So monoprotic for just one H plus that can dissociate. If we were to look back at like H2SO3, this would be a weak diprotic acid because there's 2 H pluses that can leave off of the H2SO3. So what you're really trying to recognize is if you're trying to say, well, how do I know it's diprotic or triprotic, what you'd be looking at is, do I know, like, what ion do I know how to name? Think about losing the H plus. We know how to name that as hydrogen sulfate ion or hydrogen sulfite ion. And if we lose a second H plus, it's sulfite. So just think about if you can name the underlying ion or the complementary ion, then you know that those H pluses can release to lead to that ion in solution. So like for acetic acid, we don't know how to name, like we wouldn't know how to name losing one of those hydrogens off the CH3 group. So that's one other way that we can know that those stay intact. Question 3, which compound below is a weak electrolyte and weak base in aqueous solution? So the prototype that we have for a weak base is ammonia. Molecular compound dissociates partially in water or dissociates water partially to form ammonium and hydroxide ion. So we get this partial dissociation, so we would call NH3 a weak base because we're making some hydroxide ion, and then just a little bit, so we call this a weak. So this is our prototype here. Methanol is not an acid or base. This is sodium hydroxide is a strong base, water-soluble hydroxide compound, fully dissociates the sodium ions and hydroxide ions. Copper hydroxide is insoluble. This is neither an acid or base, and it doesn't dissolve in water, so it's not appropriate to even consider that title. Going relatively fast. If there's ever confusion, feel free to chime in or ask if. What is the molarity of potassium ions in a solution prepared by diluting 125 mils of 0.250 molar K3PO4 to a total volume of 1.5 liters? Okay, so we have kind of two different sort of problems here. One, we have a dilution taking place where we could think about either M1V1 equals M2V2 or MIVI equals MFVF. So that's one approach, is using this approach here. Well, what if we forget that equation? What might we do? Well, I might just say, well, what's the number of moles? N's a symbol for moles. So the number of moles here would just be equal to 0.125 liters. So converting 125 to liters. That's 0.125 times 0.250. This M here is moles per liter. Moles of K3PO4 per liter of that solution. And so that would be, the number of moles here, 0.03125 moles of K3PO4 are present in that solution that we're diluting. And we're diluting that number of moles to 1.50 liters total volume. So the new molarity of that solution following dilution would just be 0.0208. So that's 0.0208 m K3PO4, or moles of K3PO4 per liter of the solution. Now, what's the question asking for, though? It's asking for the molarity of just the potassium ion in this solution. The solution that's an ionic compound, K3PO4, in solution would fully dissociate to 3 K pluses plus a phosphate ion. So if I have roughly 0.02 moles of K3PO4 per liter solution, you see how for every K3PO4 I get 3 K pluses. And so if I'm thinking here, for every 1 K3PO4, there's 3 K pluses. So I need to triple that molarity to get the K plus concentration. So the molarity, or the concentration of K plus, would be 0.0208 m times 3. So if we have 0.0208 moles of K3PO4, 3 times that in terms of moles of K plus. So that's going to end up being 0.0625. Let me multiply by 3. Yep, 0.0625. Okay. So now we tend to write, concentrations this way, even though we know it's not K3PO4. Like when we say it's, it was 0.250 m K3PO4, it was really always 0.750 m K plus and 0.250 m phosphate ion. But we commonly write it this way just to indicate like how the solution was prepared. But we have to know something about the solution. We have to know K3PO4 is an ionic compound, water soluble, dissociates. Oxidation number, CH2O. We're looking for the carbon. So we know by role, hydrogen should be +1 in a molecular compound, which this is. Oxygen by role should be -2. We account for our math. And then carbon actually has to be 0 here. So the only oxidation number that would add up to a neutral molecule would be 0 + 2 - 2. So the oxidation number of carbon here works out to be 0. Now sometimes we confuse ourselves. We might think, well, that's not possible. Well, it is possible. Like we saw elements in their elemental form have oxidation numbers of 0, and here carbon in this molecule has an oxidation number of 0. It's even possible to have a fractional oxidation number. Potassium +1 the collection of two oxygens minus 1, each O's oxidation number is minus a half. So it's even possible to have a fractional oxidation number. Maybe not very common, but does happen. So conductivity of a solution is proportional to the number of dissolved ions. A mole of each of the following compounds is dissolved into 10 liters of water. Which compound leads to a solution with the least conductivity? Well, let's ask this. Which solution do you guys think has the highest conductivity? Think of the highest conductivity. Which solution here has the most ions? The KF solution is K plus and F minus. The lithium carbonate is 2 lithiums and a carbonate. Sodium nitrate is a sodium and a nitrate. Remember, the polyatomic ions stay together, so we have to recognize sodium nitrate, lithium carbonate here, and the carbonate nitrate ions stay intact, but we're getting two ions from KF, we're getting 3 ions from Li2CO3, and just 2 ions from sodium nitrate. And so the highest would be lithium carbonate, because it has the most ions. Now I skipped ammonia. Ammonia is a partial dissociator, so it only partially dissociates to NH4 plus and OH minus. And so we get that partial dissociation with water because it's in aqueous solution. So we get that partial dissociation, so we get less than 2 ions. Ions are what are conducting the electricity. So the fewer ions in solution, the lower the conductivity. So B here should have the lowest conductivity. In fact, we looked at a solution of ammonia and saw that it didn't light up the light bulb very much. In solutions where we have strong electrolytes, so A, C, and D are strong electrolytes, and then ammonia is the only weak electrolyte here. Question 7, which statement's true? Are all water-soluble compounds strong electrolytes? Might sound like a true statement at first, but think about a water-soluble compound like HCl or something that's molecular, or let's think about something like ammonia or NH3. You can dissolve ammonia in water, but it doesn't fully dissociate into its ions. So not all soluble compounds are strong electrolytes. Let's look at the next statement. Are all ionic compounds water-soluble? It'd be nice if they were. We wouldn't have that solubility chart, but we know from the solubility chart some things are soluble, some things aren't. Based on the ions, we can usually predict this. And so not all ionic compounds are water-soluble. All strong electrolytes are ionic compounds. That's also not true, because like HCl is molecular, it's a strong electrolyte. We have our strong acids. Those are all molecular compounds that are strong electrolytes. So just knowing something's a strong electrolyte doesn't let you know it's ionic. So hopefully statement D is true. All water-soluble ionic compounds are strong electrolytes. And that's exactly true. So if we know a compound's ionic and we know it's water-soluble, then we know it had to ionize. That's the whole process of it being soluble in water, is each ion being surrounded by its own little water sphere. So this statement is true. And that's just something worth reinforcing, that anytime you see, it doesn't really matter what the example is. Let's say it's lead nitrate, which is water-soluble. Some lead compounds are insoluble, but this one would be soluble. That the solution is really lead 2 plus and free nitrate ion, meaning just nitrate surrounded by its own little water sphere. So question 8 is probably the hardest question on the packet, at least in terms of the math involved. So let's take a moment to look at question 8 here. We have 30 mils of 0.10 molar calcium nitrate. We have 15 milliliters of 0.2 molar sodium phosphate. They're being mixed. After the reaction is complete, which of these ions has the lowest overall concentration? Well, what we have to think about here is what reaction might take place between calcium nitrate and sodium phosphate. So the reaction would be the metathesis reaction, of course, so the exchange of the ions. Let me do something real quick. So let's take our calcium nitrate, which is water-soluble. We're told it's in solution. We know it's water-soluble. Sodium nitrate, or sodium phosphate, AQ. that these are going to react to form the insoluble compound, which would be calcium phosphate, calcium 2 plus, PO4 3 minus, so Ca3, PO4 2. This should be our solid, precipitate, and then sodium nitrate would be the byproduct, or the other product, which is water soluble. And so to work out our stoichiometry here, 2 to give us 2 phosphates on both sides. I have 3 calcium, so I need 3 calciums over here. And that's 6 nitrates and 6 sodiums, so I need 6 NaNO3s. Okay, now, at first glance, you might think that if we could identify the limiting reactant, if we can identify which of these 2 reactants is limiting, that both of the ions in that compound will go to 0. But we have to sort of think here that if one of these compounds, let's say, for example, calcium nitrate is the limiting reactant. If that's the case, then the calcium concentration should go to 0 because it's all precipitated into the product, but then the nitrate spectator ion would remain in solution. And so if we could identify the limiting reactant, then we know that the precipitated ion in that compound would go to 0, and then the other ion, like if we think about, say, if calcium nitrate is a limiting reactant, then there should be some phosphate ion remaining in solution, and there should always be sodium and nitrate ions in solution because sodium and nitrate are AQs on both sides, and they're what we would call the spectator ions in this reaction. And so now let's think about how many moles we have. So probably one way I would start this problem is just to do the 0.03 liters times 0.1 moles per liter calcium nitrate up here, and just make sure that I see this is 0.0030 moles. And then I actually have, I think, the same number of moles on the other one. 0.015 times 0.2 is also the same numerical value of moles. So the sodium nitrate moles is 0.0030 moles. And so once I see those number of moles and I see the ratio is 2 to 3, if all of the sodium phosphate reacts, I'm going to need, for every 2 of it, 3 of the calcium phosphate, which would be more than what I have. Okay, so the calcium nitrate here actually turns out to be the limiting reactant. Now, how can I know that for sure? Well, just how many moles of NaNO3 or Na3PO4 are needed to react with the 0.0030 moles of the calcium nitrate? Well, it's just for every 3 moles here of the calcium nitrate, we need 2 moles of the Na3PO4, which I think we could have done in our head, but if we just divide by 3 times 2 on the number of moles, it's 0.002. So 0.002, the 0.003 moles of the sodium phosphate reacts, and then all of the calcium nitrate reacts. So as soon as I see this, and then I kind of double check and verify that my limiting reactant checks out, that it is indeed the calcium nitrate, the calcium has to go to 0. And it's the ion that would have the lowest concentration. And so the lowest concentration here would be calcium because it's precipitated into the product and it's present in the limiting reactant. Now, if I were to ask the question, like, what is the concentration, say, of sodium plus in this reaction? Now, you might get a little confused. You might say, well, you mean before or after the reaction? I would say, well, either, because it doesn't change. So the sodium ion concentration, we could look at it from, say, here, that we have 3 sodiums per phosphate, per sodium phosphate. So I would have 0.009 moles of sodium ion. In that solution, that's 45 milliliters. Yeah?
For something like this, how organic are they going to be? Because technically, if calcium isn't in solution anymore, it's precipitated out. They're asking in the solution.
Oh, interesting. I mean, I would still say the ion of 0 is probably the lowest. I don't know. That is an interesting take. That was one that you come up after and try to argue if you get this wrong and try to get some points back. But yeah, I would still think that the one that goes to 0 would probably be the lowest, even though it's not in the solution. Yeah, that's an interesting take. You'll learn soon that even the things that are insoluble are slightly in the solution. So technically, there will always be a tiny little bit of even the thing that should be 0 in the solution. But if we're trying to calculate the sodium ion concentration, I just want to make sure we see here that the total volume is just the 15 plus the 45 mils being added together. And so we could calculate that concentration. And it's 0.2 molar. We could calculate the nitrate ion concentration if we wanted to. We could calculate the nitrate ion, which also isn't changing. So the nitrate ion would be 0.006 moles. Do you guys see how I'm getting that? Because we have 0.003 moles of calcium nitrate. There's 2 nitrates per mole of CaNO32. So the nitrate would be 0.0060 moles of nitrate divided by the same volume. It's 0.13 molar. Calcium should be 0. If we wanted to calculate the phosphate ion concentration, how would we do that? So there's, starting out in the reaction, there's 0.003 moles of phosphate ion. But then we reacted and lost 0.0020 from the amount that reacted with the calcium nitrate. And we'll divide that by the 0.045 liters. So it should be 0.001 divided by 0.045. So if you put phosphate, you come argue after the fact, I guess. Yeah, that's an interesting reading. But yeah, so of the things that aren't 0, this is the next lowest in concentration. Okay, so you'll see some problems that pop up in practice tests that just relate to calculating like ion concentrations following a reaction. And I hope you see that this is really just a chapter 3 question, just where we're using the molarity unit to get at concentrations, as opposed in chapter 3, where we're using mass and molar masses to relate to moles. Water solubility in question 9. Now, here's just like being tricky on mercury is often insoluble, but not with acetate. Every acetate compound is water soluble. So compound 3 is definitely water soluble. Sulfates are mostly soluble, but Hg2,2+ is a illicit exception, so compound 2 would be insoluble. And then compound 1 is the trick question, right? Because if we had Hg2Br2, this would be insoluble, because that's one of the exceptions. Hg2,2+ is the exception, but not Hg2+. Hg2+ with bromide is not one of the listed exceptions for bromide. So bromide chlorides and iodides are mostly soluble. This would fit into the category of being a soluble compound. And so 1 and 3 are soluble. And then the final question here, when aqueous solutions of lead chlorate and potassium sulfate are mixed, which ions are termed the spectator ions? Well, this is kind of like the question above, where we were talking about spectator ions, but if we're taking the lead chlorate and the K2SO4, the product PbSO4 is, of course, the insoluble compound, and the KClO3 is water soluble. And so if we're thinking of the solution of lead chloride, it's really lead and chlorate ions, and the K2SO4 is really 2K plus and SO4 2 minus. And so this solution here, which is going to form 2 KClO3, that the KClO3 is really 2K plus and 2ClO3 minus ions, and the lead sulfate remains intact because it's insoluble, doesn't dissociate. So the spectator ions are the unchanged ions, so that's the chlorate, and that's the K plus. And so the spectator ions here are potassium and chlorate ion. All right, so review is good. You know, like practicing these sort of problems that you can do without help, without assistance is good. So, you know, look at some daily quizzes I would recommend. You don't have to do them all. I put a bunch up really just to in my opinion, you need practice solving problems that look like test questions, where you can try those problems with the book closed. And there's not a lot of good end of chapter problems, in my opinion, where you can like close the book and do those end of chapter problems. I think they're a little too tricky a lot of times, and it's hard to know which ones are doable. So I think let's give you old exam questions, things that have been asked on an exam, but slowly throughout the semester. So if you're looking at a couple daily quizzes a week, just to make sure you're able to solve these problems without extra assistance, then I think you're going to find that come exam time, that's going to pay off. Midterm 1 went well in general. Midterm 2 can go well too, but the topics you can see here, these are a little bit trickier topics, I think, than some of the topics out of chapters 1 through 3. All right, let's take a quick overview of Chapter 5 and get into some of the Chapter 5 topics. I'm sure there's a backup alarm. I set those all the time too. Anyway, so Chapter 5 overview is about energy. So Chapter 5 is going to be about the energy changes or heat changes that accompany chemical reactions. So we're going to talk a little bit about the nature of chemical energy, the first law of thermodynamics, that energy is neither created nor destroyed through reactions. We'll talk about enthalpy. You may remember delta H's of reaction. We'll talk about those in this chapter. We'll talk about how we determine some of these values through calorimetry and how we can rearrange reactions with Hess's law to determine other reactions, delta H's, and then also get into enthalpies of formation, things we can tabulate that allow us to look up values to calculate delta H's. So tabulated enthalpies of formation will help us look up values in, like, say, an appendix or online, so we can calculate the delta H of a reaction. We also talk a little bit about bond enthalpies at the end of the chapter, and bond enthalpies also appears later in Chapter 8. So we'll talk about bond strengths and things of that nature towards the end of the chapter. Okay, so there's a couple equations that we can look at that help us maybe understand chemical energy. One is the energy associated with putting an object into motion. That's work. So work is the force you have to exert on an object to move it a certain distance. And so work is the energy associated with putting objects in motion. The next equation, these aren't necessarily equations even worth memorizing, but these are just equations that get us thinking about what we can do with energy or what energy is associated with. You can imagine the energy associated with a heat change. Like we could calculate the heat as being equal to the mass of a substance times the specific heat of a substance times the temperature change that the substance could undergo. And so in order for an object to raise its temperature, it has to absorb heat. And if an object's going to cool off, it has to emit heat. So there can be a heat change associated with the change in temperature. So this is the heat associated, with the energy associated with temperature change. I'm sure there's mechanical engineers, and there were many mechanical engineering majors. I mean, so you guys are probably almost always trying to figure out how can we get a reaction to take place that gives us the output mostly in the form of work to put objects into motion and very minimal heat formation. If you can have an engine that doesn't heat up, then you'd have less energy lost to the heating of the engine, more of the energy going into putting the object into motion. And so when we think, we probably can imagine this, that if you have so much gas in a car, you have either so much heat you can put into that engine block through running the engine just to heat it up, like where you're not moving the car, or you have so much distance that you can move the car, depending upon the efficiency and the speed that you travel, et cetera. And so depending on how much fuel you have in the car, I think you all know that if you're just going to let the car idle, then you're not going to be able to travel very far. When you decide to finally start to move, you're going to be almost out of gas. Or if you just decide you're going to immediately get in the car and start traveling, that you can probably go the maximum distance. And the reason why is you're going to be sitting there less time where you're just emitting heat and just losing heat from the combustion of the octane as it's burning in the internal combustion engine. So we can sort of imagine some of how these equations relate together in a real life situation. We also have energy associated with electrostatic attraction. So a very important equation is Coulomb's law, which relates the electrostatic attraction or repulsion of charged substances or charged ions. So if you have a negative and a positive particle, they're going to be attracted together, and the overall energy is attraction. If you have negative charges or positive charges, these are, of course, going to mean repulsion or lead to an increase of energy in that chemical system. And so if we can have two opposite charges, like an ionic compound, for example, those ions should experience a net attraction for each other. And there's an energy associated with that attraction. You can also think of the corollary. There's an energy associated with separating the charges. So if you want to separate plus and minus, it's going to take energy. If for some reason you had a scenario where you had a bunch of positive charges brought together, like the static buildup, maybe like on clothes coming out of a dryer, that they could release that static energy. They have a lot of negative charge that can be released as soon as they're able to. And so if you have positive charges and you can release them, you actually lead to a loss of energy for that system. So we can think of the chemical system of the attraction for opposite charged species or the repulsion of like charged species. And then if we start thinking a little bit in terms of what might be obvious, and we'll get into these topics later, if you could imagine increasing the magnitudes of charge, you can probably start to appreciate that if you were to compare Na plus and Cl minus, that attraction is probably going to be weaker than if we had, say, magnesium 2 plus and, let's say, sulfide ion. So if you could look at a 2 plus versus a 2 minus, probably a greater energy of attraction due to the increased charges. That's a topic we'll see more directly in chapter 8, but it ties right back to this simple equation where you can see, well, if we're going to increase the magnitudes of charge, we should get a stronger attractive force between those charges. And then one other term that's really important here is this distance term, and that because we're dividing by distance here, that the closer we can make the particles, the better. So that the closer two opposite charged particles can get, the more attraction they're going to experience. If you imagine just bigger particles that can't get as close together, they're going to experience a weaker charge. So you can already probably appreciate that if we took something like cesium iodide, that cesium iodide is going to have a weaker attraction just because cesium's a lot bigger, iodide's a lot bigger. If you don't know it yet, we'll talk about why you can pick out the cesium and iodide are bigger. So a corollary might be this, that you have these charges here, but in cesium iodide, maybe it's like this and I's like that. And then by virtue of being bigger, they have a weaker attractive force. So this one equation will help us understand some attractive forces that are present within a variety of compounds later. We'll also use it to help explain things like hydrogen bonding. If you've ever thought about or heard that two water molecules have a hydrogen bonding force of attraction, the reason why there's such a strong attractive force between the hydrogen and oxygen and adjacent water molecules is because hydrogen's really small, ends up with a relatively high positive charge on it. Oxygen's also relatively small, also has a relatively high charge, so we get a relatively strong electrostatic force of attraction due to the nature of those charges being small and relatively large. Okay, so this slide here is just kind of going back over or showing you in pictorial form that if we have opposite charged particles, a negative and a positive, let me switch pen color. So if we have a negative and a positive particle, then when those particles are brought together, they're brought closer together. So the internuclear separation is on the x-axis. So if you imagine the particles separated and then we're bringing them closer together, is going this way, and then we go down in energy. So the particles have a lower energy when they're opposite and charged, when they're brought together. And then if you imagine the same thing for two positive charged ions or two negative charged ions, we start with them far separated. That's actually where those particles are the happiest. We bring them together, the energy leads to repulsion. So this here is repulsion, and this is attraction. So like charged particles repel, opposite charged particles attract, and you can see that from the energy of attraction going down versus the energy going up for the repulsive force. And so if you had the two particles already brought together, this is where I was mentioning earlier, that if for some reason you could have a way where these particles were very close together, then separating those particles would lead to a release of energy. So energy can be released if we separate two like-charged particles that are very close together. So let's think about the first law of thermodynamics. I like to always try to think of an example of a reaction. Like we saw this reaction of hydrogen and oxygen where we physically saw and heard the explosive nature of the reaction, the flame of the reaction, the kaboom and all that. We could see that energy in the system is overall being given off. Like we can see the release of energy from that reaction taking place. Just meaning if we're thinking in terms of internal energy, our initial state had to be higher in energy, leading to a lower energy state where our products were in that chemical reaction. And the reason we can deduce this is just from the very nature that we saw the energy coming off in front of our eyes. So like anytime you can imagine a reaction taking place with like a flame, like a combustion reaction, methane burning in a, or propane gas burning in a grill, or a stove that's using natural gas, that you can physically see the flame, and the flame that you see is the energy being given off from that reaction taking place. And so you can know that basically all of our combustion reactions are going to fit this variety here, where energy is given off from those reactions as they're taking place. And so that looks like this state here, where what we have is our initial state compared to our final state, where the final state's lower in energy. We call that exothermic. That exo below, energy is being given off from the reaction where our products have a lower energy state than the reactants. And then I'm going to pass this around next time in class, but next time in class I'm going to pass around two different types of reactions that can take place. One where we can have a solution that becomes cold, and one where a solution becomes hot, because we'll see reactions can take place spontaneously that kind of go both directions. It's possible that the products could be less stable and the reaction still takes place. So just knowing the relative energy of the products doesn't necessarily help you predict if the reaction takes place or not. So you might think, you may just be looking at this saying, if I know a reaction leads to an increase in energy, does that mean the reaction cannot take place? Not necessarily. There's other factors involved. The other main factor is entropy. If anybody remembers delta G's, delta H minus T delta S, that what we're really looking at here is a delta H term. We're really looking at just the energy term here. The entropy term, the disorder term, kind of can play a role too in telling us if a reaction is spontaneous. So if a reaction actually will or will not take place, if that's a question we want to ask, that's a question you come back to later in chapter 20 in Chem 1220. So here in chapter 4, we're just really looking at the relative energy. If the products go uphill relative to the reactants, we're just calling this an endothermic reaction. Now, it just all depends on the nature of the reaction and also the circumstances. Let's think of, there's actually a really obvious or simple reaction that we can think of as being, say endothermic and being one that actually takes place under a given set of conditions. Let's think about a phase change for a minute. Let's think about water solid to water liquid. So we have ice melting. And so for this, well, I guess physical reaction, if you remember from chapter 1, for this reaction, does ice have to absorb heat or does it have to give heat off for this reaction to take place? What do you guys think? And let's even go one step further, because maybe the next one is really more obvious if we imagine going to water vapor. Because this one here, I think for sure, we're putting that on a stove and heating it up. What are we doing when we heat up the pot? We're putting energy from the stove into the water so it can give it to the water molecules to break their attractive forces in the liquid phase so they can escape into the vapor phase. And so this reaction here is definitely endothermic, meaning we have to put energy in order for that reaction to take place. But if we do, it will. We know if you put water on the stove, eventually it will come to a boil. And so just because it's endothermic, we're not going to sit there and say, well, that should never happen. If you have liquid water, it's never going to spontaneously boil, though it does disappear over time because of the vapor pressure of water. That's something we talked more about in chapter 11 later. But we know a lot of liquids have a vapor pressure, and eventually those vapors will float off. And so you can evaporate a solution even if you don't hit the boiling point. But it's not going to spontaneously boil, though, until we get to that boiling point. Same thing with melting. Melting is also endothermic. Never really going to spontaneously happen in a freezer, but so you take it out of the freezer, it will spontaneously happen. Now, why that is has everything to do with entropy that you talk about later. So when you get into the delta S term, you'll see why that's the case. A simple example on just the difference between like energy states versus like the disorder states. Like if you imagine right now, we're all like fairly spread out in the room. If I had said, let's take, this half of the room and have it be all January through July birthdays, and this half of the room have it be all August through December birthdays or whatever, that would be a very tedious process, right? It would take us a while for everybody to get up and everybody to then spread back out almost in the same amount of spread, but now in a different spot. But your energy state would be about the same. You'd be almost as far away from your nearest neighbor. Your energy state wouldn't have changed, but the disorder it would have taken a lot more energy to put you into those specific arrangements. If we wanted to say sit in order by birth date, imagine how hard that would be. In the end, you're still in the same basic energetic state. You're just as far away from the nearest human as you would have been before, but it took a lot more energy. So the energy it takes to order things together is entropy. And so there's a cost associated with ordering systems. There's a benefit you get back from disordering systems. That's something you'll talk about later. This chapter is really just getting at the delta H, or the energetic states, and talking about the energy or heat changes we're going to see that accompany chemical reactions. Now, when we think of a reaction here, let's relate this equation here. The delta H is Q plus W. Or, delta E is heat plus work. Now, this is a tricky equation to understand, but the way, an example I think we can understand this is a combustion reaction. So we have a gallon of gas in a car that can undergo so much energy change. Just like from a gallon of gas, there's so much energy that's contained in that gallon. And of that energy, we can either put it all into heat, or we can put some of it into heat, some of it into work, or we can put maximally as much as we can into work, kind of like what we were talking about earlier. But the sum of the heat and the work, these are what we call path-dependent functions. Meaning, it depends on how we undergo or use the reaction. Like cars in neutral, foot's in the accelerator, all the energy from that combustion reaction is going into heating up the engine block. Don't do this, but if you go in your car and you put it in neutral and put your foot on the accelerator, what's going to happen? The car revs up, the RPMs go really high. What do you think would happen if you keep sitting there? The engine's going to melt. Eventually, some part on the engine is going to break because it's going to get way too hot because all the energy from that reaction is going into heating up that engine block, and that's terrible. You wouldn't want to do that. And so that's just showing you that depending on how we're going to use that accelerator pedal and whether or not we're in gear or not, a path that we're choosing is going to depend on how much that energy from the combustion reaction goes into heat versus how much of it's going into putting the object into motion for work. And so heat and work are path-dependent functions, but the sum of them for the energy given off by a reaction is what we call a path-independent function. So a path-independent function doesn't matter how we carry it out. There's so much energy, like I mentioned, a gallon of octane has so much energy to give off, depending on how much octane there is. It doesn't matter how we use it, there's only so much energy to be given off. And so we'll see more examples and discussion of path-dependent versus independent, what that really means in a couple of other slides as we go along. But some of these things start to get us into, can we flip a reaction and understand something? Like if I told you that this reaction here, the solid to liquid, if I said, and it's a term we haven't seen yet, delta H, if I said the delta H was plus 6.01, let's say this unit of kilojoules, imagine that that's what it is, and that this is a path-independent function as well, the delta H, like delta E, is path-independent. And what that helps us understand is if I flip the reaction, then the sign should just flip. So then if I flip to water liquid, going to water solid, and just flip the reaction, as long as it's path independent, I can flip this and know that the delta H just goes negative. It just goes to the opposite sign, but the same numerical value. And so that's it maybe is obvious that would be the case too, but it has to be the case that this would be some path independent function. We can flip it and then understand the opposite reactions delta H. It's also really obvious that if the forward if solid to liquid was endothermic, that the liquid to solid would be exothermic. To me, this is a little bit harder to understand, but liquid molecules have energy to bounce around the solution. You have to freeze those energies out, slow those energies down. Energy has to be emitted for the liquid water molecules to freeze. And so energy being given off is exothermic. Now, let's go back a second. We talked earlier, like combustion reactions are exothermic. Those take place with a kaboom, take place with a flame. When you freeze water, it probably doesn't explode, right? So just because one reaction that's exothermic is explosive doesn't mean all reactions that are exothermic are explosive. So you put liquid water in the freezer, eventually freezes, and it just freezes. Nothing, no flame, no fire, nothing exciting happens really other than it turns into a solid. Let's talk about some sign conventions for the signs of Q and W and delta E and what those mean for a process. And so we're just thinking about the signs of heat, work, and the energy change. And so let's start with delta E. So delta E positive just means that there's a net gain in energy by the system. This was that picture previously where we had our initial state here and our final state was higher in energy. This would be delta E positive. And then that's also what we're talking about as being endothermic. Minus, like an energy lost by the system, is the exothermic reaction. That's the opposite. That's where our final state's lower in energy. Now, this chart is trying to get us to understand what a Q negative versus Q positive means, what a W negative versus W positive means. It's not necessarily trying to say that an exothermic reaction has to have both negative signs for Q and W. In case that, if we're thinking how delta E is Q plus W, that it's possible delta E can be negative, and that Q can be positive and W can be negative, just so that they add up to whatever the delta E is. So Q and W can really be any sign, any value for any delta E, such that the sum of them go to whatever delta E is. And there are a few problems in the book that I think are boring and kind of get off the topic of a chemistry class, but they'll give you some random Q values, some random W values, and have you calculate delta E, or vice versa. But here, this slide is trying to get us just to understand what it means when Q is negative. If Q is negative, it means our system lost heat. So if the system or the reaction loses heat, then that's Q negative. And so that's what we're thinking of a reaction taking place that leads the surroundings to get hot, like a combustion reaction. Like if we had our hands on that balloon, which we wouldn't want to have, our hands would get very hot, right, as that flame took place. And so that's heat being released to the reaction. The combustion reaction heating up the engine block, that's heat being released by the reaction. The engine block increasing in temperature is a sign that the heat was released by the system into the surroundings of that reaction. So Q negative means the system lost heat. Where did the heat go? To the surroundings. So the surroundings of the reaction receive that heat. And then if Q is positive, means that the system gained heat. Well, where did it get the heat from? It has to get it from its surroundings. So if a reaction's absorbing heat, it's getting them from anything that's in contact with that reaction. And the W, like work is, I think it's kind of hard to maybe at first understand if you're putting an object into motion, is that W positive or negative? And think about it this way. If you have heat to give off and you heat something else up, so you're a flame of methane, you're heating up the pot of water. So you have heat to give off, it's heating up the pot of water, so Q is negative. We're also then saying, well, let's encase that reaction and move a piston. So we're going to drive a piston with that reaction instead, and we're going to move the piston and we're going to move the car. Putting the car into motion has the same sign of negative. So W being negative means that work is being done by the system and it's pushing the surroundings. So negative means we're moving the surroundings. So we're putting the surroundings, putting the object into motion. W positive has a hard analogy to think about. It means that the work is being done on the system. It means the object is slowing down is one way, is the analogy to think of it. It's hard to picture that relative to the reaction, but a W positive just means work is being done on the system by the surroundings. So we have a system or a reaction, and then we have the surroundings of that reaction. And so what we're just trying to picture here is the system has heat to give, Q is negative, absorbs heat, Q is positive. The system puts an object into motion, W is negative, the object slowing down, W is positive. Next time, I'm going to peek here. We'll look at a couple of problems that relate to the sign of Q and W and get further into chapter 5. All right, guys, have a great day.